2. Okay.
Okay, I think maybe we can start, and I'm sure that others will join us maybe in a few minutes. Hello, everyone. Welcome to our next machine learning launch seminar. And today we are excited to have Philipp Petersen to present his work on optimal learning in high-dimensional classification problems. Philipp is a tenure-track assistant professor for machine learning at the Mathematical Institute of the University of Vienna. Before that, he completed a postdoc position at the University of Oxford, and he did his PhD at the Technical University of Berlin. His research focuses on the interplay between deep neural networks and numerical analysis, and his particular interests are on expressivity of various architectures of deep neural networks, structural challenges for the optimization and training of deep neural networks. So we are very excited for your talk, Philipp, and thank you again. The stage is yours.
Thank you very much for the introduction, and thank you very much also for the invitation. Yeah, I want to talk about learning today, especially high-dimensional learning. And in fact, as you already kind of alluded to, it's going to be learning with neural networks. So it's most of the talk is joint work with Felix Vogtländer, who's a long-term collaborator of mine. So So the problem that I'm talking about is mostly classification. When I say classification, I also mean mostly just binary classification. So I'll be talking about something of the sort like what you see in this figure. I'll have two classes, let's say blue circles and red crosses. I've seen a bunch of them, and now I would like to find the label for a new observation, which now here's the question mark. And I mean, when I look at this image, then what I'm doing in my mind is I'm kind of separating this into two regions, which I would like basically color one of them red and one of them blue. And then depending on which of the sides of maybe the intersection between these regions this question mark lies, I would say it's probably red or blue. And I don't know if there's a definite answer to this question. Probably everyone here has a different solution. I would probably say it's red. But this intuition that you're kind of drawing a line between them, that's kind of something that I will use a lot. So this is the setup that I'm working with. I'll have observations. So these are x's, these are the positions, and y's, these are the labels, and they follow some distribution. So I put here xi's and yi's are just the positions and labels, and the distribution is going to be a joint probability distribution. It's going to be called P. That's probably going to be it's a small p in this case. And I have n of them. These are these circles and crosses. And then what I'm looking for is some function, which I'm usually going to be calling y hat. And this function should predict the label of something new that's observed. And it would be nice if this would be a good function. And a good function is one that has a small error in expectation on unseen, or just on any data. So we write here this risk of the prediction rule. It's just basically the probability of misclassification. So there's going to be a y, which is the correct label, and the probability that I misclassify. That one is the risk. I want this to be small. And for this problem already, there is a correct solution. There is a so-called Bayes classifier, and that's the one that I want. Yeah, so the Bayes classifier, the one that minimizes this thing, that is an indicator function. So it's going to be, it's an indicator. So I write this here as this 1 of G star. And this set G star is going to be all x's, so that the probability of observing label 1 given this x is larger or equal than 1/2. So that's a region in the space, and this region is what I should be labeling everything as 1. This region marks everything that should be labeled as 1 by the perfect classifier, the base classifier. So now I'm trying to find that one. That's basically the problem of binary classification. And so in practice, there may be a couple of things that make this problem easier or harder. So these are like 3 standard classification problems. Yeah, first two are the ISIS data set, and the last one is, wait a second, IRIS, not ISIS, IRIS data set, and the last one is MNIST. And so what makes these problems harder or simpler? Well, one of the first things is the complexity of this G star. Yeah, the region that I was talking about, the region that I'm trying to find, if this is a very complicated region, then we would think that this is probably also a complicated classification problem. Yeah, so we see it here in these 2 top IRIS data sets. In the first one, I drew a classification boundary, which of course is not the truth because I didn't know it. I just estimated this, which is, I would say, maybe something like a nice function. Whereas in the middle, the function is a bit more rough. But you could also think of things that have more holes in it and so on and so forth. And then we would think that this is probably a complex region, whereas the one on the left isn't complex. And the one on the very right is also not a complex region. I would not call this complex. We'll talk more about what I mean by complexity, but now we have an intuitive kind of understanding of what complexity means. So that is one of the factors that makes a classification problem harder or not so hard. A second one is noise. If there's a probability of observing misclassified data, then obviously that makes the problem harder. So for example, I mean, this is not the case because in none of these problems is anything misclassified. But you could, if you just look at the center image, there's one thing that looks like an outlier. It's not, yeah, it's correctly classified. But if these would appear quite a lot, then we would say maybe the problem is, it could be that the problem is noisy, then it would be a harder problem. And the last thing is something that's called margin. If these classes are separated by really a positive distance, like you can very clearly see in the MNIST problem, which is a pretty simple problem. If you're just separating zeros and ones, you basically just have to look at the center pixel, at least in this problem. Then they're quite well separated. And then we would also think that's an easier problem than in the center, where both classes are very close to each other. Okay, so these are 3 things. And let's make this a bit more mathematical. There is already a framework to study this, these types of classification problems, know how hard they are. And this was introduced by Tsibakov. So he has 2 conditions, and they quantify how complicated or how hard classification is. So the first thing is a noise condition. So let's break down what we see here. There is first an eta, a function appearing. And eta is the probability of observing 1 given x. So that's this, we've seen this before. Yeah, where this thing is larger than 1/2, we want to classify as 1. Where it's less than 1/2, we want to classify as 0. Yeah. Where it's equal to 1/2, those are the points where you observe with the same probability both labels. So it's just a coin flip, and you cannot really make a decision. But these things also mark the decision region between the 2 classes. So what this noise condition tells or asks from us is that there aren't that many points that are very close to that region 1/2. So you look here at the eta and all the points that are close to 1/2, and then those where this is where the distance is less than t, this should decay quite quickly with t if q is large. And so then this noise condition would say if q is large, then there's not that much bad noise, and if q is small, then it's a noisy problem. So that's taking care of the noise. And the second condition that is used here is this complexity condition again. So now we're trying to sort of quantify how complex are these regions. And I'm just taking a set of possible regions, and then I'm quantifying just how large this possible set of regions is. And this is done here through the entropy. And in fact, this is the so-called entropy with bracketing, which at this point we don't really need to introduce. And we don't really need to care about what it is. So basically, it's a measure that explains to us how large of a set is this curly G, this calligraphic G. So G is a set of sets. And with delta, which is, well, basically the width of a delta net that you need, that describes this bracketing entropy. With delta going to 0, I want this complexity to not explode too quickly. So R should be small. If R is small, then it's not that complex. If R is large, then it's a very complex set. Okay. Those are the two conditions that Sivakov is using. And with this alone, you can already explain how hard the learning problem is. Here's the result. So the result basically states there is a set of sets. We call this mathcal n. And if I'm performing empirical risk minimization over this set, or over the indicator functions of this set, then trying to find that set that satisfies all of the data that I observe. I'm doing empirical risk minimization here, then there is a learning bound. Basically, it says in the worst case, so you look at all possible distributions joint distributions, the risk of that empirical risk minimizer that I found minus the best thing that I could do, I could have done, it decays at this rate. And if you look at this expression here, then let's think of basically no noise, so Q going to infinity, then this first thing is basically 1, and this is basically 2. So it's 1 divided by, and then it's 2 minus 1, so it's 1 divided by 1 plus R. So you see, if you have very small complexity, R is very small, then you get here a learning rate that's basically n to the minus 1, which is pretty much the best you can always do. And if R, the complexity is quite large, then it's a slower bound. It's a slower rate. We'll later also see that this cannot be improved. So this is basically as good as you can do. It really only depends on these two parameters. Okay, but there's a bit of a problem with this approach, because it requires us to perform empirical risk minimization over some but existing set of sets. And that's not what anybody does in practice, right? So in practice, we want to do, maybe we want to train a neural net. That's at least what I want to do. So let's see if these rates can also be achieved with neural networks. So very briefly, let me explain basically my notation for neural nets. So a neural network is going to be a map, and I'll usually call them large phi or something like that. And they map from RD, input dimension is D, to RNL. So NL, that's the size of the Lth layer. So these networks have L layer, large L layers. There's an activation function. In this talk is, I think, always the ReLU. But basically the results, I think most of them would probably hold with other activation functions as well. These N1 to NLs, these are always going to be the number of neurons. I will have some affine linear transforms. So they're large T, L, and they are affine linear, obviously, and they map from RNL minus 1 to RNL. So basically transform the signal from one layer to the next. And the whole network is then given as just this composition. First, you apply one of the affine linear transforms, then you apply coordinate-wise this row, and then the next affine linear transform, so on and so forth. In my setup here, at the very end, we do not apply an activation function. Okay, so this is going to be the set. This is going to be a neural network in my talk, and for this, we can now hopefully first show how well they can represent these binary classification problems that we're looking at, and then later we see how well they can learn this. So for the part where I'm just talking about how well I can represent those classifier functions, I will be a bit more general because we can. So I told you, so now this is unfortunately a little bit different notation. So first I use this 1 lowercase b, now I have the chi lowercase b, that means the same thing. So both are characteristic functions of a set B. And the functions that I'm going to look up at in the next couple of slides are of this form. So they are a function f that is given as f1 plus this characteristic function f2. If you want to be back in the binary classification regime, just set f2 equal to 1 and f1 equal to 0. So these are going to be the functions, and I will measure this complexity that I talked about at the very beginning. I will measure this by just looking at how complex is the boundary of these sets B. So if these are very complex boundaries, then I also will probably have them complex sets B. So I'll measure this always through the regularity of the boundary of B. And we'll see how this is done. But you can think of, for example, I'm saying the boundary is going to be CK, so K times continuously differentiable functions, or analytic functions, something like this. This is going to be the type of regularity that I will use. Okay, so here's already a little bit older result. If we're having, well, if we have a set B in the unit cube, the functions of this form as before, and fi, so f1 and f2 are both also ck regular, and the boundary is ck regular as well. Well, then I can represent or approximate this function f quite efficiently with a neural net. So in fact, there exists a series of neural nets, phi n, and they have a certain number of weights. So weights meaning the non-zero entries of these matrices and shift and bias parts. And they approximate this function f with this error, mn, that's the number of weights, to the minus k divided by 2d minus 1. And there's also a certain number of layers that I need for this. And it only depends on k, the smoothness, and d, the dimension. Both of these numbers are optimal, and you cannot get away with significantly fewer layers, and you can also not get away with fewer weights to get the same approximation rate. And this is, I think it's quite an interesting result because it tells us that, okay, I have these functions and they may be non-smooth, and I can basically approximate them as if they were smooth. Yeah, so it's not made explicit here, but this k, this could actually be also, it could be chosen differently. It could be chosen in such a way that this would be the optimal rate for the smoothness here. So basically the approximation rate here is the optimal thing that you could do, even if there were no discontinuity, no jump. Yeah, so basically it tells us that neural nets can resolve jumps without any cost. And the number of layers is also interesting because it's k, so the smoothness divided by d. So basically it tells us to get this optimal approximation rate, if the smoothness is quite high, we need deeper networks. But then we can get away with fewer weights. Yeah, because this is kind of high level information, deep networks can decode it. So it's a quite intuitively nice result. So I wanted to very briefly explain to you how we proved this, just so we get the idea, and we'll also later do it again for a different result than similar proof. So what we do first is we kind of cut out, and I'll explain at a later point in this talk, how one cuts out regions from this overall function that I'm trying to approximate. And these regions are taken such that, well, the function that I then end up with is some kind of horizon function. So a function that it has a jump along basically a curve in all coordinates but one. So in a sense, not in a sense, I can write it as this characteristic function again of a set, and then the first coordinate, say, could be also a different coordinate, is bounded by a smooth function of all the other coordinates. That's how they locally look like them. And the nice thing is this I can rewrite using the Heaviside function. So the Heaviside function of just, well, this smooth function minus x1 is exactly the same thing as this characteristic function up here. But that's quite nice, because everything in here is kind of stuff that I can do with neural nets. I can do a subtraction. This is a smooth function, so it's basically a classical neural network approximation, even though we had to reprove this because there was no result with finite depth, which is the one we wanted. And then the Heaviside function is just, well, you have one ReLU, and then you stop it at some point. And that gives you something like Heaviside function, if you then rescale. And that's basically how one can prove this. Yeah? So it's not very intuitively, it should be pretty clear. Now, there's also learning that you can do with these. And this is not our result. This is actually something that was done based on this result that I just told you. So the result that I'm now talking about is the one by Kim, Owen, and Kim. And what they showed is that if you're now performing empirical risk minimization, but not using the 0-1 loss like we had before in the result by Tsibakov, but the hinge loss, then you can, in fact, get something that looks quite good at the beginning. And we'll also later see that it is quite good, but currently we don't know what's optimal here. So the hinge loss is basically this kind of thing. So if the input is -1, then it's 1 or 2, it's just a positive constant. And if the input is 1, then it's 0. Yeah, the input, always the multiplication of the predicted label and the true label. Then if they have different signs, then it will be -1. If they have the same sign, then it will be 1. And if you do this, and you do this over all kind of functions where the discontinuity is CK regular, then these errors, they decay of this kind of rate. And there are also some log factors. But the Q is again the noise from the Tsibakov condition, the K is the smoothness, and D, that's that I mentioned. So if you think of letting Q go to infinity again, let's say we have no noise, Q can be chosen arbitrarily large, then basically all the Q terms kind of vanish. And we have something like K divided by K plus D minus 1. Wait a second, that doesn't make any sense. What did you say? No, that doesn't make sense. I'm wondering if it's, I probably cannot just simply get rid of all the Q's that easily. And the point is, the point that I'm trying to make now is that there's still a D plus 1 in the denominator. And that means if we have a very large dimension, then this is going to be a very, very hard problem. And we might not want that because in practice we don't see that. But we can learn those, but we see this pretty strong cursive dimension here. And I want to do two things now. I want to tell you that in high dimensions, that's the name of the talk, in high dimensions, we can still do classification And I will also want to tell you that this problem is, I will also show you how optimal this problem is by just showing you that there are lower bounds. So first of all, I want to cast this in a more general setup. I also want to turn on the light in my room real quick. So, sorry about that. So we can do everything a little bit more general and then give some lower bounds and then show how close to these lower bounds we are. So basically everything was based on these horizon functions. So let's just define for a general class of functions, let's call it C, and a set of horizon functions, which are just all the functions HB, so that they can be written like here. So basically those functions where they have a jump along a curve that is in this C. And all the functions with these kinds of decision boundaries are just those functions that locally look like these functions. Yeah, where I could locally just take out a small little cube, and then on this cube, the function would look like that. Those are now the functions with C regular decision boundaries. You could put C equal to CK, and you would be in the case from before. You would have functions with CK boundaries. Now, for our result, the following concept is really crucial, which is the covering entropy of a set. So assuming you have a metric space, doesn't actually have to be a metric space, but in this talk it will be. So there's a distance function, and there's a set X, and I have a subset of this set X, which is called K. Now, for an epsilon, I call a subset of this K an epsilon net if, well, every point in K has a distance no more than epsilon to one of the elements in G epsilon. Or in other words, I could put all these blue little circles over my set K. Blue circles have a diameter of 2 epsilon. And I cover all of K, and the blue crosses are the elements in G epsilon. And then the entropy is just the logarithm of the smallest of these epsilon nets. Yes, and I will use this kind of notion now to tell us how, what's the best we can achieve in learning. So here's the result. Basically, I'm just trying to learn horizon functions because that's simpler than learning just the whole classification, just functions with that boundary. And I'm mostly interested in the lower bounds. That's the first thing. The second thing is I'm now considering the noiseless case. Again, I'm doing lower bounds, so noiseless should actually be easier. So if I'm getting a lower bound for that, it will also hold for the noisy case. Why is it important to have lower bounds for noiseless case? Well, because sometimes we just don't know if the lower bounds that we compute for a noisy case, if they're due to the noise or due to the actual hardness of the decision boundaries. Well, I want to find out something about the decision boundaries. It could be that if I use noisy data, that there's just a lower bound that I cannot break. And that is actually not so unlikely, because there are some examples, like, for example, if you want to learn smooth functions and you have perfectly accurate data, you get a certain quite fast rate. But as soon as you introduce just any kind of Gaussian noise, you immediately drop to a much lower rate. But it's the same problem. Just one has noise. So that's why we want to have lower bound in the case of noiseless data. And here it is. So you take AM, basically all possible learning algorithms from sampled data to the hypothesis set, to the set of horizon functions with that class C boundaries. And then I can bound from below and above the expected error of the reconstruction from this A. A would just be one of those algorithms. But in the best case, so I take the inf over all possible learning algorithms. Then I look at the worst case over all the H in this concept class HC and look at the expected error. And this is upper bounded and lower bounded. The lower bound is m to the minus alpha over b plus 1. The upper bound is beta divided by b plus 1. And these alphas and betas, they come just from the entropy of C, yeah, the set of the boundaries. So how complex are the boundaries? This describes exactly how hard this learning problem is. So this is the entropy MCL1 of this class C that describes the boundaries in the L1 norm. And if it's lower bounded by 1 over alpha, it's lower bounded by 1 over alpha and it's upper bounded by 1 over beta. Epsilon to the minus. Okay, and this describes exactly how hard these problems are. How would one prove that? Well, it's actually, there is a related result for the density estimation problems. Density estimation problems are described, the hardness of those is described, like here, by the entropies. Now, this is a result due to Barron and Young. And so we basically have to now reformulate this result to these horizon function problems. And we basically use two equalities. So first of all, we can find for each horizon function, HB1, we can find an associated density. It's defined here. It's not so important how it looks like. But the distances between them have the same norm. But this one is the Hellinger distance and the other one is the L2 distance. The good thing is if they have the same norm, then they also have the same packing entropies. Yeah, if you have all the function in the horizon function class, to each of those you have one of the densities and they have all the same distances, then they have both sets have the same packing or covering entropies. And the second thing that we use is that the horizon functions, the distance of them in L2 squared is actually the same as the distance in L1 between just the boundaries. Yeah, because the boundaries, I mean, what's the difference, the squared difference between two piecewise constant functions? Well, it's the region between them, where they don't coincide. Well, this is actually exactly the region between the two functions that describe the boundary. And that's why the squared L2 distance here is actually the same as L1. And so now you see that we can get this entropy of the densities is the same as the entropy of the L2 of the horizon functions is then the same as the L1 entropy of the functions B1 at the jump curves. Yeah, and this is the result that we then use. So you see it's quite related to the one that I showed before. Here, Barron and Young, they showed if you have a set of densities P on some space, and you can upper and lower bound the covering entropies in the Hellinger distance of those, then you can also have some upper and lower bounds on the expected squared Hellinger distance between any kind of estimator and the true estimator. So we basically have to reformulate this theorem to our setup using all these equalities that I said before, that I explained before. And that's how we got this. Okay. So these lower bounds, we want to have them with, we can't do better than this, but we want to still find this with empirical risk minimization. The lower bound is over all possible estimators. There's no guarantee now that we could also do it with empirical risk minimization. So first of all, the problem that we already know a solution to with empirical risk minimization by the result by Kim and Kim that I talked about, we can now judge how close to optimal this is using our lower bound. So the L1 entropy of CK regular functions, the function that this was about, is epsilon to the minus k over d. Now, that implies an optimal learning rate for CK decision boundaries of m to the minus k, and then divided by k plus d half plus 1/2. That's just me plugging this in to our result. And the previous bound was this one here, m to the minus k over k plus d plus 1. And you see is quite close to the optimal one, up to this factor 1/2 around this d plus 1. So yeah, it gets reasonably close. For large k, for really smooth boundaries, it gets quite close to the optimal one. But anyway, this result also still suffers from this curse of dimension. You see the d in here that I've already mentioned before. And so now I want to find a result that works in high dimensions and where we get quite close to this optimal lower bound that we've just established.
Sorry, Philip, is it okay if I ask a question here?
Absolutely.
So like the Q that we had that quantified noise, right? So like maybe I missed that, but like what happened to noise here?
I erased the Q here in this bound because so my lower bound is for no noise.
I see.
So basically I let also in the upper bound result by Kim and Kim, I let the noise, the Q go to infinity and then noted the value that they get here. Yeah, this is, yeah, so I don't know if there's a gap. Well, okay, I should be careful here. I think one could basically get the noisy case is already included. Maybe not in Kim and Kim. I don't know if they do it, but I don't want to say they don't. But definitely, Imaitsumi and Fukumitsu, they study the noisy case as well. And they show that their lower upper bounds are, I think, again, close to tight when you assume noisy data. So basically, I'm now showing that their results are also close to tight when you have noiseless data. Yeah.
Got it. Thank you.
So what happens in high dimensions? Okay, so now I'm just looking at a different type of function class. And the classical one that machine learning and neural network people like to look at if it's a high dimensional problem is this Baron class. So this is a class of functions, and you describe them through the inverse Fourier transform. So basically you say, okay, I can represent my f as this. So f hat being the Fourier transform as an inverse Fourier transform. And I want that f hat has some kind of bounded moment. I just call the moment of f cf. So I multiply it in Fourier with this psi. And then I'm saying that f is in gamma c. Gamma c is the Baron class with constant c if cf is bounded from above by c. Okay, and it's a great class because it has some nice properties. The main property of it is that for every function in this function class, or basically this actually holds for every function f, you can approximate with a neural net in the R2 norm, and the error is bounded by 2 times, and then you have the norm, so the CF divided by square root of n. And the neural net has 2 layers, n neurons. Now, so it's an approximation rate that's pretty slow, but it doesn't depend on the dimension, which is nice. And of course, yeah, there's some assumption on the activation function, but ReLU, for example, works. Now, okay, we can think of the case where the boundary would be of this form. And so these functions, they are functions that usually do not vary in too many directions at the same time. Functions with kind of bounded variation. So it makes a bit of sense that they could describe jump curves, because they wouldn't be incredibly complex, and they would only locally change in a couple of directions. For me, it is a bit intuitive that this is something that the decision boundary would at any given point only depend on quite few variables, but they might change. Yeah, so the variables that the decision depends on could be different points, but at each point it may be our own. Maybe these are only a few. But okay, this is just an intuitive explanation why I think it could be a model. But also, it's actually not that restrictive. We have we showed in our paper as well that actually even functions that have the cusps are functions that are locally of Barron regularity. So it's quite a nice set of functions. Yeah. So if we look at functions that are locally of Barron regularity, we would now expect that our problem can maybe be solved without a cursive dimension. And that's true. Yeah, so if f is the characteristic function of a set B and B has Barron class boundary, then we find a neural net. It's called phi. 4 layers is what we need. And it can be taken such that you can just take any kind of measure, but maybe for now, think of the Lebesgue measure or uniform measure. The measure of everything that's misclassified, so where my true solution does not coincide with the neural net, that measure goes to 0. And it goes to 0 with the rate that's n to the minus then less than alpha. Okay, alpha depends on the measure. Half. If you have a uniform measure, then alpha is equal to 1. There's a c, which is for the Lebesgue measure also 1. Otherwise, it can be something else. I can talk about these alphas and c's later, but currently just think of alpha as 1 and c as 1. There's some multiplicative dimension dependence on the dimension, and there's a k. And the k just means in how many pieces do I need to separate my underlying function f so that it's actually locally of Barron class. Yeah, so locally means there are these cubes on which it looks like Barron. How many of them do I need? That's the k. Okay, and so this is quite nice because it bounds the probability of misclassification with a rate, and the rate is independent of the dimension. And it's, for an approximation theoretical person like me, it's actually quite a nice result because it's an arbitrarily high dimensional problem, and it's discontinuous. It's not a super nice function. It's actually, the function that I'm learning here is not nice at all. And I can still like approximate this quite well without actually paying a lot for it. Okay, so I have to just very quickly check the time. Okay, so I should probably, yeah. But I'm still going to go through this proof, but quickly. So if we localize as before, which I could now describe, but probably don't want to do this now, then we have the same setup as before. Yeah, locally this looks like a Barron function, and those I can, without cursive dimension, approximate quite well with just very few neural nets. That's the result of Barron. And so basically, I need to just now use my trick from before. Yeah, write this characteristic function as a heavy side. I know how to do the heavy side. These gammas I can do with a 1-layer neural net. And that's basically it. Now the harder part, why I need actually 4 layers, is this localization step, because we have this complicated curve and I need to localize. Okay. But now I don't want to talk about this. I can maybe talk about it at the end of the talk if there's still time. So how do we get now this lower bound? Well, I told you we need the entropies. Okay. We need 2 entropies. Well, basically, we only need the L1 entropy, but I will need for a different result later also the L infinity entropy. So let's say we have the L1 entropy. I mean, we need a lower bound on the L1, we need an upper bound on L infinity. And these we've just computed. And they are these numbers. Yeah? The L infinity entropy of the Barron class is epsilon to the minus 2d divided by 2 plus d. There's also a log factor. And we have a lower bound on the L1, which is more or less the same. And if we were now to plug these things into our result, our lower bound in the noiseless case for these classification problems with barren regular boundary, we would end up with a lower bound on learning, which is for some expression m to the -1 over, then there's something here. But if you think of d being quite large, then this is basically m to the -1 over 3. So 1/3 is the rate that we can get, and we can't really do better for these function classes. Okay. So the question is, can we actually do it? And yes, we can. There is a very, very nice result by Kimon and Kim that is also applicable in our case. So assume the following. You have a target constant h. Okay, in our case, this is this indicator function. You have a set of sets of functions. They should be bounded in some way. And we know that for them, the hinge loss expected error goes to 0. Yeah, this is basically nothing else than our approximation result that we use. If our approximation error goes to 0, then this goes to 0 as well. We need to bound the bracketing entropies of these things. Good thing is, I didn't want to introduce the bracketing entropy. I don't have to, because the bracketing entropy is upper bounded by the L infinity entropy. And this we know. So we also have an upper bound for this. And then, okay, there's again some kind of noise condition, but we can assume here Q to be arbitrarily large because we say no noise. Then we know that the empirical risk minimizer performs in a certain way and performs exactly like described here. So this error, the expected error decays as this epsilon to the -m with epsilon. M is the worst of the two bounds, delta m and am. Okay, now we just have to plug it in. But if we plug in our bounds, what do we end up with? I hope it's on the next slide. Yes. If we take the right networks, well, I've just computed the right numbers here. If we take networks of exactly this size, and we perform empirical risk minimization over these neural nets with 4 layers, those number of neurons, this number of weights, and the weights should be bounded, then we end up with this learning bound in the hinge loss. And it's m to the -1 over 3. There's a small kappa that can be chosen as small as you want. So it's basically exactly the optimal lower bound. And I think it's quite a nice result because even it tells you pretty precisely how to choose the number of neurons and number of weights to get the perfect or close to perfect learning of these functions. Okay, so let me conclude, because I think I should, yeah. Let me conclude. I think one thing that is really interesting, these classification problems are high dimensional, arbitrarily high dimensional, and discontinuous along potentially, yeah, some really non-trivial curves. But we can approximate them very well with neural nets. We don't see a curse of dimension. And the greater, what's also really nice is that we can do empirical risk minimization, the thing that we're always doing, and we also don't see a curse of dimension in this this learning rate. And okay, we found a theoretically optimal learning rate, and we were close to it. So we don't get it exactly. We're not exactly at the optimal one, but we're pretty close. For dimension d going to infinity, we're actually pretty much there. Yeah, and this is basically all I want to tell you about classification. Here are some references that I've talked about today. So the first one is on the approximation of the Sperrin class. It also mentions estimation, but the estimation bound that we had in this paper is very far from optimal. And in fact, we only came up later with how to get closer to this optimal rate. That's what this talk was mostly about. Then here I have optimal approximation of piecewise smooth functions, the result from the very beginning. And this is the new one, optimal learning in high dimensions. And then I have here the 3 results from the literature that are also used. And I'd be very happy to answer some questions.
Fantastic. Thank you so much, Philip. fantastic talk. So let's open the floor to any questions. Okay, I can start. So one thing that was quite interesting was the number of, so if we have this decision boundary that we would like to approximate, like, and you had this k locally barren regions, right? Like you need to be able to make that assumption. And you, the figure was really nice that showed even a function that is not differentiable satisfies that barren condition. But like, I really don't have the good intuition about like what is this k for, like as d goes to infinity, how crazy this k is getting.
Yeah.
Because
I mean, that's a good point. So before I try to answer this question, I should give some credit, because actually this, the fact that this cusp regions and so on are also barren functions, this was actually not our idea. This is just due to one reviewer who gave this very nice comment. So I don't know who that person is, but that was very nice. So how does everything depend on D? Yeah, so I think in the worst case, it might actually scale quite badly with D. If you have a function, if you think of just a very simple one, like the sphere, which is, yeah, basically you need, if you want to cover this so that it's just horizon functions, I think you probably need for, I guess, for each dimension at least one cube, or at least two cubes, which wouldn't be so bad actually, now that I think about it. Yeah, would actually not be that bad. But I can imagine that you sometimes need probably quite a lot of cubes in high dimensions to cover these things. And it might actually scale exponentially with the dimension. But what I'm thinking is that most problems will not have a boundary that curves in all dimensions. So this, I'm thinking, so this is the same thinking as barren functions. These are high dimensional functions, but most of the times not all dimensions really count. And that's what I'm thinking is also on a slightly larger scale probably happening. So you have horizon functions, a lot of them, but in most directions, this, yeah, it's hard to verbalize this thought, but yeah, I'm thinking in most problems you'll probably just have very few regions that you need. But I agree that it's hard to imagine this kind of theoretical concept to say what would be a function that has just a very few, for which I just need very few cubes to cover it so that it is actually a horizon, locally horizon. Yeah. So
a follow-up kind of question on that, right? Am I understanding this correctly, that then if there is a low dimensional structure to the decision boundary in the d-dimensional space, even if D is very large, this k doesn't become an issue. So if we had this assumption that your the decision boundary has a low dimensional structure in this high dimension, embedded in this high dimensional space, then the results would hold nicely, right? Still.
yes. So I think maybe we have to differentiate between two things. I mean, if there's a low dimensionality in the decision boundaries again, then it would just basically manifest itself, I think, in a small entropy of these decision boundaries, which would make the classification problem simpler. In the main theorem, we don't even need to be able to approximate these with nets. We just need to be able to, they just need to have a small entropy, and then there exists a learning algorithm, but this might be incredibly complex. So if, as you say, there is some lower dimensional structure, something that reduces complexity, then we can definitely learn easier. But the second problem is, how can we do it with neural nets? And there, at least, we needed to do these localization steps, and they cost a bit. If we do these localization steps, maybe we can go back to this image again. Yeah, these things, they cost, I mean, linearly, basically, in the number of these steps, but we still need to do it. So yeah, you can probably come up with a function that just curves randomly around in space a lot and makes our life really, really hard. Even though it's locally super nice. Yeah, I don't know. I haven't thought this through. So there might be something that actually prevents the function from being really bad if it's locally quite nice. But the problem is we have two worlds that clash a bit. One is usually this local description of regularity, and then there's the more geometric notion that these functions aren't supposed to curve around too much, which is then reflected in these k, in the number of k's. And so, yeah, it's hard to bring these two things together at the moment for me.
That's fine. Are there any? Is there any other questions? Okay, if not, I have another one. This might be very naive, but I missed what's so special about 4 layers.
Aha.
Right. Yeah.
I also kind of promised to explain this more. So, yeah. So why do we have 4? I'm not sure if 4 is necessary. I cannot prove to you that we need 4 for this problem. But yeah, it's sufficient. So we need 2 to basically do these horizon functions. Yeah, because I told you, okay, we need to have, here you see it, you have this heavy side that needs 1 layer, and you need the gamma, the function, the barren function itself, which needs another layer. So you have already 2 hidden layers. And now I said we need to do this localization step. Okay, and the localization step works kind of along these lines. There is a way to build with neural nets these kind of box functions. And that's only in 1D. But that needs 1 layer. And now you can make this into a higher dimensional box function by adding a couple of those and subtracting the number of, and then add 1, so that this actually is only 1 if all of the xi's are in their respective boxes. And then you add another row though, because otherwise it would be negative, but you don't want that. So that adds another layer. And then you can add 1 more layer to that and make this into a kind of multiplication, but a binary multiplication. So it only works as a binary multiplication with a box. Yeah, so if you input to this, so basically this computational unit here that takes this cube or something, adds another input y, subtracts 1, applies the ReLU, is a binary multiplication with this thing, if y itself is 1. Okay, so now this thing has 3 hidden layers, and that's the same as saying 4 layers in my language. So we have this thing, and we input it at some point into this y, we input the output of the other thing. So, and we do it one step before the last. So actually everything together has 4 layers. But it's really because of this localization step. I'm not 100% sure if this is necessary. I haven't seen anything else. And obviously this is a very technical construction that has very little to do with any application, because of course in application never would you see something like this. But this is what we needed, and we had to do 4 layers. Yeah.
Now I get it. Yeah, awesome. Thank you. Okay, if there are no more questions, maybe let's thank our speaker again, everyone. If you can unmute and thank our speaker, that would be great. Thank you, Philipp.
Thank you very much. Again,
Thank you very much.
Thank
you.
Fantastic.
Yeah, then I guess I wish you a great rest of the day.